Alright, so like last time like right after streaming, I thought a bit about it and I had some notes. Yeah, these are the notes. Ignore everything below. Fix gamestate.clone to also copy is P1 turn. Because like I realized that like this wasn't being copied. I was like kind of like after the stream I was kind of replaying I was like kind of imagining my search function. The search, like the whole point of last time was get status, get diff. Okay, yeah, just that thing changed. The whole point of last time was this function right here, right? I'll just highlight it. 53 GG, like this function right here, right? Sorry. Like this whole function right here, like this is like what we did yeah, yesterday, right? So I was kind of like thinking about this and like kind of like imagining like the search play out, and I realized from doing that that like how do we kind of keep track of like whose turn it is, right? And that's like kind of right here, like it's player 1's turn, then player 2's turn, player 1's turn, and so on, each level of the tree alternating, right? But I realized that like the way that this clone was done actually is a bug. Like it doesn't actually respect that. Like it will kind of always do it. Like the point is that like clone has to also like preserve whose turn it is. And like if I look at the clone, right? Like the first thing was fix the game state clone, like to also copy that. I realized it was not being copied. Like v game state dot ts, and then kind of like let's go to the bottom and look at clone. Like we're kind of like we're showing a copy, right? But the only thing we're doing right here in these lines highlighted is just we're only kind of copying the cells. But we also have to do is copy the have to also do like copy dot is what's it called? Is p1. So like right now, like these are two static, and the only kind of instance, like the only like these are static variables, there's like the instance fields. This one right here, and then cells we kind of copied in the nested for loop, but we just have to copy that, and that's it. But I realized that I forgot to do that last time, so it's a good thing I caught that. Is p turn equals to this dot, and then same thing, right? Wait, what? Yeah, it really annoys me in Vim, or like what you have in your copy is like kind of like when you swap it in for something, then the thing which you overruled gets kind of in your copy. Never mind, whatever. I'm just bad at Vim. Okay, so then that's kind of a crucial thing, right? Like we have to do copy.cells, like we handle copy.cells and we handle copy.is turn, and those are two things. Like I forgot this line right here. I forgot this line. Okay, so I think that handles that. And the next thing I realized is like it's just a simplification I can do, right? Like when we're creating terminal MC like Monte Carlo tree nodes, right? Like this, create node, like the base case, terminal case. Yes, right, this function right here, right? This function right here, create node. Like if you look at the, if we look at like this whole thing right here, like this block right here, this if block, if the game is over, right? If the game is terminal, then we're kind of doing a switch here. Now, one thing I realized that we can do is like, this is probably correct because I convinced myself of the correctness, but I realized that there's a simplification I can do, right? Like the draw case, obviously like the terminal value is 0, right? But then for both of these cases, the value has to be -1. Like there's no need for these things. Why? Because as I explained here, right? So like when it's like, again, like yesterday, like I just use like keep.google for like just writing some notes, like bunch of running shit right here. But like the point is that like fixed game, so simplified creating terminal MC nodes terminal to always be -1, right? And like this is kind of why. Like first of all, before I do this, let me just kind of like go away because like, that's kind of like the answer. Let me kind of explain why, right? So when we create the node, like when we're doing like this function right here, like because this is the main thing we're gonna like do right now, like the actual heart of it, the actual like do, which kind of invokes it a bunch of like these number of times. But like the whole point is to get a policy, improved policy, right? Now like first what we do is we create the node, right? Like we're given like ultimately this is like the whole point of this, right? Like the whole point of this like whole MCT, like this whole file MCTS.ts. Yep, the TS is really Monte Carlo tree search. .ts for TypeScript and tree search. But like the whole point of this function is given a game state, we get a policy. Now, of course, we can just like plug in the model and like get a policy right there from the network, but we kind of like do the whole tree search to get an improved policy, right? Now, if the game state is terminal, actually, let me just add that right there. Actually, no, like one thing is the game state that we pass in, it cannot be terminal. It has to be an ongoing, like the game state dot like the game state's game status, right? It has to be an ongoing thing. So we know that like create node, like the root node can never like enter this if block. This if block right here, we can never enter it when we create the root node, because like if the game is already over, then what's the point of even like getting a policy? Like there is no policy to be gotten when the game's over. So it's only like kind of, it's like we know already that this game state status is like a live game. A live game, like when I say live, I mean like it's live. It's not finished. So like the game status is not ongoing. So like when we're like the only time when we actually hit this block is for the case where like the game state, like whatever kind of node it's attached to, like Monte Carlo tree node, that is not a terminal node. Like it's for like the node that we're creating, that we're going to create in this if block in return, is a terminal node. It's not a root node, because again, there's no point in ever like calling this function on a root node, because there's no point calling this function on a terminal node because the game's already over. Okay, I've said that like 50 times, but the point is that like this happens like somewhere that's not root. So like that means since it's not the root, like the main thing about a root in a tree is a root has no parents. It's like the topmost elements in a tree, not like a Monte Carlo, it's any tree, and like it's like by the definition of being a tree, right? But if it's a terminal node, it's not a root node. That means it has a parent. That means that like, so like that means that like, let's just say this node is terminal and it's like player 2's turn. I'm saying 2 because of what I saw in the like this thing right here. But like let's say it's player 2's turn and the game is over. That means that player 1 won. Like if we hit this if block, right? And we find out that like the game status is finished, that means that the player whose move it is to go, right? Like that means that like it has a parent, like it's not a root. And like what a root of a tree means, like a root has no parents. But this state right here, like the node, like the point is that like when we're calling create node, we're calling create node right here. Like this is a line where we use it. So like right now we have like some node. Let's just say it's player 1. Like the node's game states is P1 turn is true. That means this node is for player 1's turn. Now player 1, right? So player 1 makes a move, okay? Player 1 makes a move. And then, wait, what's this? Did I just like do something? I don't know what I did. Let me just quit that. Get diff. Sorry about that. Player, get diff. I think I accidentally like made a, sorry about that. Where was I? 53. Okay, yeah, perfect. So right here, right, when we're like, so like, let's say that like it's player 1's turn, like the node has a game state, and the game state's player 1 turn is true. So like the node, this node is for player 1's turn is true. Right? I mean, it's player 1's turn in this node, and then like we find like we use the UCB score right here, and we decide what move is most promising, and then we let's just say that we enter this block. Like let's just say that we we want to make this move. We copy the state and then we apply this move, and then now we're in a new state. So we create that state. So after making the move, the game ends. Now, what this means, at least in games like Connect 4, because like some games there's like a word called misery or something. I don't know how to pronounce it, but like misery. Wait, never mind. The point is that like in games like Connect 4, the person who makes a move, like let's say a person makes a move and the game ends, that means that they made the winning move. That's kind of like the idea behind it. So like, let's say player 1 is here, player 1 makes a move, we apply the move, and then we find out that like after applying the move, the resulting game state after applying the move is a game over, right? And let's say that's not a draw. It's a decisive result. It's not a draw, it's decisive. Well, that means that like this player, whose turn it is, player 1, after applying this move, now like the game state status is player 1 won. They win. Whosever turn it is, if they make a move and then the game ends decisively, that means that they must have won. And that means that when we're creating the node, we have to return -1. Why? Like let's say player 1 makes a move, and then the next game state dot like, and then if you call it a game status, we'd get like game state dot p11, and then whose turn is it in next state? Well, when we apply the move, we we swap the turn. So if it's player 1's move, he applies the move, it becomes player 2's turn. So from player 2's perspective, it's -1. Therefore, like these two things, terminal value will always be -1. That's kind of like the idea. And I wrote that there. Simplify creating like this terminal nodes, terminal values always be -1, because if decisive, that means not draw, then the current player turn must be lost because the previous player made winning move. Like example, player 1 moves to win, then game state looks like P2 turn, outcome P11. So from player 2's perspective, in this node, it's -1. And then we can swap player 1 into, like, the whole point is that like this rule always holds, regardless of player. So let's just make the simplification there. I mean, this is still correct. I'm pretty sure this is still correct, but we can do a bit better. But actually, I'm not sure we should, to be honest, because like, what if like, actually, the thing is, like, yes, I could technically always make it to -1, but in BumperCoins, like, one thing I'm thinking of, like, what if there's like a suicidal move? Like in Connect 4, if you drop a coin, you can't lose. Like, you can never lose by dropping a coin. I mean, let me rephrase that. Like, if you make the move and then the game ends, you could have never lost in Connect 4. But technically in BumperCoins, I don't think that's true. Like, what if, like, the king, you flick a king, it hits another person's coin, that coin hits a wall, and hits you back and you lose, and the game ends, then, like, wait, so sorry, I think this whole thing right here, this whole simplification might not hold for BumperCoins in very niche edge cases, like very, very tricky edge cases. So I think that actually, let's just think. Yeah, actually, maybe that this is actually better. Maybe I was getting too clever right there. Because let's just say that like right here, Control Y to scroll up. Let's just say that like this move that you take ends up becoming like a suicidal move. Again, suicidal moves cannot exist in Connect 4. Like, when I say suicidal move, I mean like you make a move and then by taking the game state and applying the move, the next game state means the game ended decisively. So obviously in Connect 4, that can never happen. You can't just like place a coin and then the game ends with your loss. No, it doesn't work like that. Because you could do a proof by contradiction, say, well, if the game ended, it must have already been over prior to me making a move. But that means that like that's a contradiction because game can only end at most one time. The point is like, wait, what is the point? Yeah, the point is that like this thing applies for Connect 4, like we could do the simplification where we set to -1 always, but then if it's a suicidal move, then that we cannot set it to -1. It should be 1. So let's like think about like, let's see how this thing is more robust. I believe it's more generalizable because I want this to be a framework, not just for Connect 4, but for any 2-player turn-based game. Well, maybe not that, but it should at least support BumperCoins. So let's pretend that this move is suicidal. Again, this cannot exist. No suicidal moves can exist in Connect 4, but they could exist in BumperCoins. So let's try that out, right? So let's say that like it's again player one's turn. I like it to be player one's turn. Player one gets to go first. So player one's turn. Now it chooses an unexplored edge. Again, because like this node does not exist, JavaScript unique, JavaScript like undefined. If it's undefined, it evaluates to false. So then like we're kind of like testing out a new move that we haven't expanded out yet. So then we take the game state and then we apply the move. So player one makes a move, and let's pretend that by making that move, player one loses. So then we're creating the node. Now the game status is the case is that player 2 won because player 1's thing was suicidal. And then the game state's turn, right? So whose turn is it in this game state? Well, it's player 2's turn because it was player 1's turn there. And when you apply the move, that toggles whose turn it is. So then now it's player 2's turn and player 2 won. So we're in player 2 won, and this player 1's turn is false, so it becomes 1. Right? So then the terminal value becomes 1, whereas right here, I was saying that we always be -1. But that's actually less robust in the case of suicidal moves. Actually, I think that the notes I jotted down yesterday, while they work for Connect 4, they do not actually work for BumperCoins. So I think that like actually kind of like enumerating all the, like writing out every single possibility and like kind of, I do think that like this is the proper way like to make it more generalizable. So I think that like, yeah, so I mean, I'm glad I talked that out. Even though it ended up changing nothing, like, it's kind of good to have this good to think about this. Good thought experiment. So yeah, I'll just exit that. Get status. Clear too much clutter. Get diff. Okay, so then clone. At least that's a crucial bug that I fixed. Clone, and then this just we just realized that 7 squared is sufficient. 49. Let's double it just for good. Actually, 100 is a very nice number because like ultimately what you're doing, you're normalizing, right? Actually, let me just quit this. Like when you're normalizing, yeah, like the improved policy is simply normalized counts. So this function right here, right? Like what is this going to be? Well, I believe this is precisely this number right here, and dividing by 100 is like literally percent, cent being 100, and then per meaning divide. So I think that's like percent is a pretty nice way of dividing it. Or if we can be super clever, we can make it like 128 or some power of 2, so you could like do some like bit shift like fanciness, like shift to the right by like some at k where this number is 2 to the k, right? If you right shift by 2, that's same as dividing by, if you right shift by 1, that's same as dividing by 2. Right shift by 2, dividing by 4, and so forth. But 100 is a nice number. Wait, what's the number which they did? Number of simulations? Oh, that's AlphaGo paper. Each MCTS used 25 simulations. Each iteration, 100 episodes of self-play. So like each episode like gets a bunch of training data. You do that many times. Like, that's a lot. Each MCTS used 25 simulations. So this 25, at least for us, becomes 100. Okay, that's, I mean, same order of magnitude, just a factor of 4 difference. No problem. And then this, okay, let me just commit that. Get all. Get diff staged. Yep, that's correct. Status, get commit, fix, game state, cloning to copy whose turn it is. Status, get push. Okay, and then let's just make sure that it, let's just kind of view our change. I like to always like view the change whenever I make some commit. It's just pretty satisfying, like kind of seeing that like my work gets actually kind of, you know, pushed to GitHub. Yep, we respect, we also copy alternatives, and then I guess this doesn't, it's not really, it's kind of a, not really kind of part of the commit, like logically. It's just kind of unrelated thing I did. Just, I mean, we haven't used this yet, to be honest. Actually, now we're about to do it now. So now, finally, like, our comment is only like this much. Everything is like actually there. Just our comment. So now, it is time to delete the comments and it's time to actually do, it is time to do MCTS. Okay. Takes in game state returns a policy. Creates the, I have no idea what was going on there. Probably gonna say create the root, create the root, and then do the simulations. But okay, that's kind of obvious. Let's delete that kind of line. So first we create the root 0. Create node returns a node and the value. Yeah, we don't really care about. We just care about 0, the actual node. Then for this many times we return search. What is search parameters taken? It says root model. Let's just make sure that's correct. Yep, it just takes in the node and the model. Perfect. So then this is actually correct. Okay. Use the root and the edge weights to, I'm just reading this out loud, to create an improved policy. Look at the edges, num, wizards, and normalize over them. Correct. Normalize, we divide by the 100, that variable at the top and return a policy. Okay, well, let's do that then. So we have to create a new policy, right? Let's just open up the file for policy just to refresh my memory. Get diff. I just deleted some comment lines. Okay. Now for the, yeah, so now we have to kind of open this and then also control E policy.ts. So policy, the construction, the whole point is this function, this thing right here. This moves in probability. So let's copy that line. Okay, so then let's let moves and probabilities equal to new list. Okay, so now for let the edge, we have to iterate over all the edges, right? Like look at the edges, num, wizards, normalize over them. Okay, yeah. So for let edge of the root dot, what's that called? So the root is a node and then the edges, yeah, just root dot edges, which are MC edges right here, right? For root dot edges, for let edge of the edges, and then return new policy where we pass in the this thing. It's a wrapper on the central data structure, the move and probabilities. Okay. So let move equals, actually no, let's just do it in one shot, right? This thing right here dot push let's create some space. So we push and then what we want to do is edge dot move edge dot prob, right? Edge dot, yeah, exactly. These two lines right here. Move edge dot prob. Let's normalize the prob, sorry. Edge dot move. Edge dot prob divided by, because we're normalizing, right? And we have to normalize by this. Now, why am I normalizing by this, right? Because like ultimately, like, let's just say that like whiteboard, let's say that like this is our root and our root has been visited 7 times. Like this edge has been visited 4 times, this edge 2 times, this one 1. Like each action, like this one is very unlikely. This one is double likely, and that one's double if that. Like it's a power series of 2. So like we're like this one would be like 4/7. We're gonna explore this edge, sample it like 4/7 probability, 2/7, and then 1/7. Like 4/7 for this edge, 2/7 for that edge, and then 1/7 for that edge. Each edge is like the action that we take, right? The edge has the move in it. So like if you have 4, 2, 1, like add up to 7. So like we visited this root 7 times, and then when we visit it, when we visit a node, each time, every visit, we visit one node, we also select one edge and visit them. So they're kind of paired up. Like if you look at like if you look at the actual search, right? If you look at this search function at the end of it, right? Like if you see here, I mean, I already talked about it before, but like you see these 2 lines right here, the edge num visits and the node num visits. Like whenever like we visit an edge, we also like do the bookkeeping right there. So like ultimately, like every single time the search is called on the node, that node gets a num visits, except in the case where it's terminal. Wait. Here it doesn't get num visits plus plus. Well, no, that's completely fine, right? Because like we only like, cause like the whole point is that like this num visits, right? Like this num visits, like 7 equals all of the like the num visits for any like we're given like some. Let's kind of delete the circle. We're given like some node here, and let's just say that it has x. Like we visited x times. Whenever we visit this, we have to like visit a child, right? Except in terminal case. So like whatever like let's say that like we kind of like we have some we're gonna visit this node, right? It has some number x, right? And after we visit it, it gets x plus 1. Once we're done visiting, it's like we visit this, and then like we decide that this is the best edge to take after comparing UCB scores. So like this one gets plus 1, that one gets plus 1. So like the whole point is that like the visit count for this node is like kind of the sum of all of its edges, but in a leaf node, a terminal node, there are no edges, right? It's just empty. It's just a node, and like there's no more children, there's no more actions you can take because the game's already ended. So it doesn't make sense to have any number there. It should always be 0 because like I mean like once you hit it, that's the end of the road. Like there's no more children to explore. And like the whole point is that as we're exploring the children, like child actions hitting child states, like that's when we do num visits. Okay, that's perfectly fine. But anyways, the whole point. Wait, they're making changes. Get diff. Claire. Get diff. Okay, I'm just doing this function right here. Okay, great. Policy. Wait, what? Div caps lock on? No, I don't. The whole point I was talking about is why, like, I'm just trying to explain like why we're dividing by this, right? The whole point is that like at the end, like when we're doing search, we're searching on the root, right? And every time we do the search, as I mentioned, whenever we're calling search on a node that's not terminal, and the root, as I mentioned before, is never terminal. Like the root node is never terminal because like that's just stupid. Like why are we trying to get an improved policy when like the game's already over, right? Only if the game is live, if it's ongoing, does it make sense to like consider like the actions we can take and refine them. So this root node, I've already mentioned prior, like a few minutes ago, is never terminal. So like always, whenever we call search on the root node, we increment its num visits by 1. So like if we call search on the root how many times? Well, precisely this number of times. So we end up visiting the root that many times. Like all this plus plus in line 83, it'll be plus plus 100 times. Where 100, of course, is the cart assignment of this variable. So yeah, that's kind of like the idea. And then, so we just kind of, that's like the sum, so we can just kind of divide by that. And that's it. I really think that's all. I think that we're finished with Monte Carlo tree search, unless like, I mean, maybe there's some bugs, who knows, probably. I mean, I don't know, but like, at least like the gist of it, in these 135 lines, I think that like, I'm quite like, I do think that like this is, I think I've like kind of faithfully kind of implemented, no, not this. These 22, like these 22 lines of, I guess, Python pseudocode, it took me like 135 lines, but I do think that like this is like the gist of it right here. Actually, technically 118 lines, because this right here is actually corresponds to like this and that right there. Like they kind of like, I'm just kind of wrapping all these things inside a nice function. But yeah, I think that's it. Let me just make sure it compiles. Errors. Oh, is this some let bullshit? 1, 2, 3, G. Yep, let the root. Okay, good. Now let's see how many errors we have. New. Wait, why do I have a new? Okay, let's fix that. What line? 130. Okay, just an empty list. One thing I'm worried about is one thing I'm kind of a bit concerned about, let me add everything, is like immutability, or like what if like things are getting mutated? Like I have to make sure that like game states are being cloned. What about moves? Make sure this compiles. Okay, good, it compiles. Status. Okay. Okay, let's just look at this file. So like, let's make sure that the moves are distinct, or are new moves. Let's see, search. Where do we like create the edges? Well, yeah, when we create the nodes, let's go create node, make sure it get policy and value. Move and prob. Game status. Get policy, or that's net.ts. Yeah, we import that function, right? Look, what is going on here? Oh, we're just kind of unwrapping this and stuffing it into edges. Let's look at get policy and value. I know I did this like a few streams ago. Or right here, get policy and value. We filter illegal moves. Get legal moves. So game state, well, let me just look at that. Game state. Make sure that like game state, like I want to make sure that like when we're kind of getting legal moves, good, new move. That is crucial, right? I wanted to make sure that like it would be terrible if like we're like kind of returning like, you know, like the same move again. I want to make sure that like that each time we call it get legal moves, we're creating like a new move, a separate object. And this is turns a Boolean, so it's a primitive, and then C is just a number, the column index, again a primitive. So like, I just want to make sure that like there's no kind of like, you know, like those bugs where like two objects point to the same thing, and by changing one thing, like you end up like kind of changing it elsewhere, right? Like the same, like making sure that it's like some pointer. Anyways, I was just a bit okay. So I think that's good. Status clear. Get staged. Get this staged. So then let's see. I just stuck in the let here. It's pretty glad that like my kind of initial sketch, which I commented, basically compiled with almost like just only a few lines, like just actually returning a policy, and it just kind of worked. I hope it just works. I think we're done with Monte Carlo tree search. I think it's time for actual self-play now. I mean, can it really be this easy? I don't know. Let me just recap the changes I'm about to commit, the stage changes that I've committed but not pushed yet. I mean, not committed, I haven't committed them, I just staged them. It's a staging arena. Area, so like, okay, root. So the root, we just create the root, sure, why not? And then we, 100 times, or whatever this number is, we just do a bunch of searches. Each time, like every search, we're basically creating one more node in our graph. So we'll have like, 101 nodes, where it's 100 non-roots and one root. Each search, we're kind of like, you know, just doing Monte Carlo tree search, one iteration of it, and then we're kind of like bubbling all the way down until we kind of hit an unexplored edge, and then we explore it by kind of creating a new node and evaluating and bubbling it up, propagating it, back propagation. So we do that, and by doing that, we get to get our improved policy based on how many times we've visited the root, like the edges from the root. So we kind of look at the edges from the root, and then we're building up the policy data, moves and probabilities, and then we just kind of like put the actual move. Again, this move is a new move. It's not like it's new. It's from get legal moves. It's a new move. It is the move, and then the move basically has a column index, and then it also has the probability. This probability comes from wait, no, this is wrong. This is wrong. Prob is what we don't care about. I mean, sorry, prob is guiding us, but what we care about is edge.num visits. It's not the prob, it's the num. Like we're normalizing over num. Yeah, edges num visits normal. Yeah, num visits. What am I doing? V Monte Carlo tree search, or GG, and then GG just means like telling Wim to go to the top of the file. Edge.num visits. YE yank that word. Okay, good. I fixed this bug. Num visits, and then divided by the state's num visits, which happens to be this. If I want, I can call it like, I can even call it like root.num visits too, but we know that equals that. It's the same thing. Actually, let's just be very kind of like, let's be very kind of, let's just be very kind of upright about, like very kind of like, we can do that. Wait, no, sorry. Oh, yeah. We can do this. Why by root? Because, like, we know that, like, this... Actually, let me just kind of, like, I could just comment that. I'll kind of copy this comment. Is there any need to say that? Just to like explain that I know what I'm talking about. Just a nice little comment right there. I'll put this comment in its separate line. Okay. Okay, so now we're just same thing. Like what we're doing is we have like the move. We need the move and the prob. And the probability is simply like kind of the relative, basically like each edge from the root has been visited a bunch of times. And like how do we kind of rank the edges? Well, we kind of do them based on the relative importance of like each edge's visits. Again, like kind of like this whole thing where like we visited that 4, 2, and 1, like 7 total. So it's 4 7, 2 7, 1 7. They're probabilities, like the improved probabilities from the Monte Carlo improved. Like the tree search gives us improvement. Because again, like we have the edge.probs already, but like by doing this MCTS, by building out the tree, we're kind of refining and getting a new distribution, which is hopefully more accurate, more refined. So yeah, edge.num visits divided by that. Okay, perfect. Status, clear, get diff. Let's see the change. I added a comment, okay. And then edge.move and then edge.num visits. Great, get add all. Clear, get diff, staged. Okay, so root, same thing. So what comment? Wait, why is there a... Oh yeah, I can delete that comment. That was just like commented from policy. Let me just make sure it compiles. Okay, great. Just deleted that comment. Deleting a comment's perfectly acceptable. Stage stuff. Delete comments, create, delete. Let the root just add the word let. Yep, the policy data, empty list, and then we just kind of create the like from the edges we kind of extract the number of times visited, kind of normalize over the total, which again I explained that plenty of times. And then we kind of give it the move and then the new refined probability of the move based on like how much it's been visited relative to all its neighbor sibling edges. And then we kind of like pack the move and its improved probability. And then from that, we get our policy. And that is it. That is the do. We're doing MCTS. And that should be, that's more or less like our policy improvement. We did the MCTS and we returned the new improved MCTS, improved policy. Git status, git commit use MCTS search to get improved policy untested. Gotta add that disclaimer. MCTS search to improved policy untested. I could say initial, untested, all these words to suggest that I've just written my thoughts down, but I haven't really like stepped through them or like actually like seen them in action yet. But okay. Git status, git push. Clear. Status, git pull. I just do git pull sometimes just to make sure. I don't know why I do it. Git log. Just to search to get improved policy untested. Yep, gotta have the untested there. Just like initial untested, I'm putting untested. Untested and uncontested. All right. Yeah, okay. So let's refresh. And then yep, here it is. Untested. Gotta specify it's untested. Yep, I already went over that. Delete some comments, some empty lines, and yeah, just our new policy based on normalizing the edges, num visits, normalizing them. Okay, I think that's a good stopping point. Pretty, not really much done, because like yesterday's stream was like the bulk of it, like doing the search, but we fixed the clone, and then yeah, we basically did this yesterday, and then I kind of like fixed cloning when we were kind of next day. Like I kind of fixed the cloning states. So now our SP would have the correct whose turn it is information. And then I did not do any terminal simplifications. and I just did the I did the whole this whole kind of like, see this whole MCTS.py thing where like they kind of search the, like S is kind of like the start state, which is the root, which I call it, in the do MCTS function I wrote. And they do this a bunch of times, same thing, for loop, just do it like 100 times in my case. And then like we kind of sample from that, like MCTS.py, like gives us the policy, right? We're actually using it, we like kind of randomly sample from it. But that's like in the actual policy iteration, like the actual pit, like the actual like executing episodes. Like how many episodes? Like they kind of like do that a bunch of times. Like 100 episodes. Like each episode basically self-play. The bot plays against it to get generate training data. And then in each specific episode, in every single turn, 25. I do 100. I'm not sure I'll do 100 episodes of self-play. I mean, I don't really know how important, like, I don't really, like, again, I've never ever, like, kind of, like, I've never, like, kind of done this before. So it's, like, what I can do is, like, do, like, one episode, see how long it takes, and then, like, I can do this off-stream. I can just kind of, like, kind of, like, run some tests, like, test some numbers. Like, I have 100. I can, like, toggle these numbers and, like, kind of see how long it takes and just kind of like maybe like do it overnight. Like I think like he model took around 3 days. Like I think he just like let it run overnight and then woke up and like I don't know. Or was that like some other guy? Never mind. Wow, 3 days. That's a lot. Is there like a graph? Because I know in like AlphaGo, like in the paper, like there's like a graph that shows the elo kind of improve. Like initially, like it really improves, and then it kind of hits a steady state. It kind of like kind of like a logistic curve or whatever, like population size. They eventually hit carrying capacity. Like I guess they call it like saturation, right? Yeah, saturate. Eventually, like initially, I think it gets the playing strength increases pretty dramatically, and then it kind of like peters out at some point. You get diminishing returns, then you stop training. I guess it's specific to like many things, including like the actual game, like Othello. I mean, I'm doing Connect 4, 6x6, 6x7, similar size, 3 I don't know. I don't know how long this will take me. Maybe I can like do it in the cloud or something. Like, I don't know. But yeah, like all that's left now, like now in theory, I've done search. All that's left is actually like self-play. Like now that we kind of like have a function that like we can like leverage our search to get improved policy, and then all we have to do is like policy iteration, like doing self-play, and that's kind of like the end. We just take the bots, have the network play against itself a whole bunch of times, and then generate training data, train a model to get a stronger model, have the stronger model like and repeat, like, and we keep doing that until we kind of get a very strong model, and that's it. That's all that's left. Self-play. But I mean, I feel that I can like I feel that this is a good stopping point before actually jumping into this. But this is actually like, I mean, I've read the pseudocode before. It's like very it's extremely kind of like I mean, it's extremely, I wouldn't even say easy to just like what it's doing. Like if you actually kind of like read this function, and then kind of like the key thing is execute episode, like to generate a bunch of training examples. Like we're kind of concatenating it into examples. Like this is kind of like the heart of it. Like that's it. Like that's it. I guess I can talk. Actually, yeah. I'll just like kind of talk about this, I guess, and then end the stream for now. Actually, I kind of feel like ending right now. Like it says like, believe it or not, like we have all the elements required to train. And like what elements? 2 things. Number 1, the neural network, which I did several streams ago, and number 2, which I mainly did yesterday, last stream, is like the actual tree search, where we're the nice search function where we do MCTS, and like those 2 are like kind of like the bulk. Number 1, we need a neural network. Obviously, unsurprisingly, there's at the core of things, right? I mean, I did a lot of talking about this. I did a ton of anyways, but like this was done. And this, I mean, I've only written my thoughts down. I've verified that it compiles, but I haven't actually like troubleshooted this yet, like step through it, I think, a debugger. But in theory, like this is done, or at least it's like I have a good grasp on this. And now it's time to like put everything together like this. Actually, do I really want to read it? Well, okay, how about this? I'll just talk about this a single episode, right? An episode is when like a bot plays itself, like it's self play, right? So initially we start off at the starting state, okay? Then we're going to generate empty training data here. So what is the training data, right? The training data, like examples, is a list of something. Well, what is in the list, right? There's three things: a state, a policy, and a reward, right? Like if you kind of like look here, right? Training example of this: the state, the policy, and then this hasn't been like, it's either +1, meaning that like the state, remember the game state has like the state knows, like the state can be player one's turn or player two's turn, right? So if player one wins, then for all the states belonging to player one's turn, this will be +1. And for the remaining half, for like the remaining like plus or -1, you know, like if it's odd means the remaining states, it would be -1, right? +1, current player eventually wins the game, ls -1. Yeah, so like it's from the perspective of like, again, S of T, inside it, implicit in the state, is whose turn it is. Like you need to know the current player, right? So plus like, so like if we have like like 2,000 of such training examples and like someone won decisive, half of them would have like +1, and then the other half interleaved would have -1. And if it's draw, then all these would be 0. That's the example which we're training the data from, right? Again, here's the complete training algorithm. We initialize your neural network with random weights, which I did like long time ago. It's saved in like the model folder. It has like the JSON topology and like the bin, like the binary file for like the weights. Random policy. Again, I did that a long time ago. I called like and value network. It has like two heads, the policy head and the value head. In Connect 4, it would be like 7 dense unit, like 7 softmax, because 7 columns. And value, again, like a 10H activation function. So like it caps it between -1 for the other player whose turn it not is. -1 means that like that person wins. That means that the current player loses is -1. So everything is from the perspective of the current player. It'll be the first image plane. +1 means the current player wins. -1 means the current player loses. 0 means it draws. At least that's kind of like what the value is. Like what what the network estimates the evaluation to be of a game state. In each iteration, we play a number of games of self-play. So a single game of self-play is called an episode, and that is what I'm going to like talk about here just before ending the stream. You play a number of games. The whole point is to generate training data. So in each turn, we perform a fixed number of simulations. Again, like that's 100 in my case from the current state, S of T. We pick a move by sampling from the improved policy, which my function do MCTS returns the improved policy, like a normalized over the edges num visits. This gives a training sample. I mentioned how we assign the rewards. The reward is filled in at the end of the game because like initially we have the state in the improved policy, but we actually don't know like who won. At the end, we actually assign that, or right here, like we assign the rewards once the game ends. Like at the end, so either player 1 won or player 2 won. Right? So I think like, anyways, that's it. We've signed at the end. In fact, just this paragraph already kind of like mentions everything that this code does. To have iteration, we just train it. Now training, we have to actually like do a bit of data expansion. Like there is some expansion we can do. Like, you know how like in convolutional images, like people do rotations and like they kind of do a bit of translations. Like they kind of like take the training data for a CNN and they like kind of expand it, like they like kind of like move it around a bit, they rotate it a bit, like kind of like to make it more robust. Like that's like kind of like here symmetry. Like there is some symmetry in both in BumperCoins and Connect 4 too. Like for example, like the point is that like when we get a bunch of training example, we can actually double, quadruple, or some power of 2, like rotation reflection for Go. I think it's like 4 or 8, I believe. Like they have like 4 times. Or like if you have like K training data in the game, it can become 4K or 8K. I think it's 8K for like Go and chess maybe. Like some power of 2 it is. Like for example, like the point is that like we generate a bunch of like examples, training examples that we actually like train the net with. Like we just train the net with these examples. And then we actually can generate some more examples. And well, I was gonna talk about, I guess I'm talking about everything now, but And actually, in the future, we can delete these lines because, like, the latest version of AlphaZero doesn't even do this pitting. It just always assumes the new network's better than the old one. But I'm getting off topic. Oh yeah, I'll mention this. Like, the whole symmetry, I mean, the symmetry, temperature, I don't know anything about, to be honest. History of state. Oh yeah, I remember when I read this, that this was, this is actually wrong, I think. Like, yeah, I remember when I first read them, like, wait, no, this is wrong. Okay, I'm like kind of scatterbrained right now, but like, since Go is not completely observable in the current state of the board, the neural network takes in the last 7 time steps. This is a feature of the game itself, and other games such as chess and Othello would only require the current board's input. Now, technically, that should not be correct because, like, in chess, and like in chess at least, like, I'm not sure, but like, I guess the history of the state is a part of the state, right? So, I mean, it could be just technicalities, but like, in chess, if the king is moved, then like it could castle. Actually, I think that might be passed in the unit plane in an image stack. So maybe that's actually wrong. I mean, maybe that's correct. Maybe this is correct. Because like the point is that like sometimes like in chess, like you need to know like if there's been a 3-4 repetition or if like the king is moved preventing castling or something. But I think that's passed inside the image plane as like a, like, you know, there's an image plane, like image plane is input to neural network. I think that like you can have like a, like all like in this given plane, like every single entry is like some constant. And that could be like an indicator variable, like 0, 1 or something. Like 0 means like no, like kind of like a Boolean type thing, or like something like that. I don't know. But anyways, actually let's skip this. The whole point is symmetry, right? Like what I'm saying is that when we're generating these examples, we can actually like in the train function, we can take our examples and like for connect for, I think like double them. Like what am I talking about this? Let's say that like we have like kind of like white here, black, black, white, like this, right? Or let's just say that like, let's say that it is black's turn. Let's say that it's black's turn. Wait, no, well, okay, yeah, let's just say that like, let's just say it is, let's say that it is black's turn to move, right? So, sorry, let's say it's black's turn to move. So where should black move, right? Well, if you've played Connect 4, you know that black better move here, right? It better move there. Because if white moves there, then black would have to like defend against Connect 4 here to block this. And it would have to defend against Connect 4 here. It's like a double attack, like a fork in chess. Like something has got to give. Like if you block this, white will win this way. If you block this, white will win this way or it'll win this way, but you can't control both, right? So in this situation, the policy, well, let's call this like column 0, column 1, column 2, column 3, column 4, column 5, column 6, right? So here, black has to like kind of do there, right? So like this prob would be like 0, 0, 0, 1, 0. Wait, let's just pretend now that we only have 6 columns. Let's just pretend that like, we only have 6 columns. Oops. Like the reason I'm saying that is so that like 7 is like kind of symmetric, right? So like right now, like the point is what I'm saying is like black is compelled to place a blocking thing right here to block a chain of 3 from forming because that is a forced win for white, right? So that's like its policy. Its policy vector looks like this, right? So like that's like this is the game state S, which is like this box right here. And this is like the policy vector here, like for like if black plays a perfect play, right? Now what we can do to make the game kind of more robust, and we can actually flip it, right? We can actually like kind of like do this. Here, 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 right? So if this were a situation where like this is like, wait, so this is 5, 0, right? So then like 0, okay, 5, 4, 3, 2, 1, 0, right? So now if we have like this, like calls S prime, right? where prime is like kind of flipped. Like we kind of like we take it and we flip it about this. We flip it about like kind of like flip it like this. Like this goes here, and like that goes there. Like we kind of like we flip it about this vertical axis. Then like we get this state, and the policy here, like black is compelled to kind of block here. So what this vector would look like is like 0, 0, 1, 0, 0, 0. And that's why I said let's make this have 6 columns, right, instead of 7. Because if there were 7, then like, you know, like if you look at like this P prime, right? If you compare these two, then like they're not equal. It's like these two are equal. These two are like, if you look like these like the first two and the last two are 0 in both cases, right? First two and last two are fine. But if you look at the middle two for an even number, then in this case, like that's 0, 1, whereas this case is 1, 0. That's why I chose an even number of columns. So like the point is that like we have like a like for example, like we have like kind of like S comma P, and then let's call this outcome like just whatever, like let's just say it ends in a draw. SP0, that's one training example. And the other, which we kind of like use a symmetry to generate, is like this one. S prime, P prime. Let's pretend that this is a draw, I don't know. Or just we can call this like X, where X is the same X, the same outcome. Now, technically the coloring doesn't matter. Like this black and white could be interchangeable, because remember, like the whole point that the neural network takes is the current player, right? From neural network, again, has 2 image stacks. It's like from the current player's perspective. So like the color does not matter. It's just like whose turn it is. Like it's the current player. Player 1's turn, player 2 turn, it just whose turn it is. Like in this configuration, whosever turn it is, like the coins for their turn are encoded on the first plane, and the coins for the player's not turn is encoded in the second image plane. And that's all. Okay, I got sidetracked, but the whole point is that like that's where this whole like kind of symmetry goes. Like the whole point of symmetry is that we can gain invariance, rotation, reflection, right? Oh, that's another thing too. Networks called reflected. Okay. When MCTS reaches a leaf node, the current neural network is called the reflected or rotated versions board to exploit the symmetry. Oh. So I guess I have more work to do then. Temperature, I'm not going to do. History, I mean, you don't need it for BumperCoins or Connect 4. That's irrelevant. Temperature, to be honest, I don't really understand this, so I'm just going to skip that. Symmetry, I will do. Asynchronous, whatever. I mean, I'm not going to do anything in parallel. JavaScript is single-threaded, or Node.js is single-threaded. I mean, yeah, I'm just going to do it single-threaded, whatever, compute power. I don't know about that yet. I'll try to run it on my MacBook Air, and then like if it takes too long, I might just like look for alternatives. Neural network design, yeah, like I'm not using residual connections. I'm just using a very simple like 2-layer convolutional network for Connect 4. I think I might use more CN convolutional layers for BumperCoins because it's a bigger board. Yeah, so just symmetries left. So I guess I have some more work to do in the leaf node, like in a like when we're creating a leaf node right here, right? Like when we're doing get policy and value for game state in this model, we have to like flip a coin. Like this game state is either like our game state or it's like the flipped version. So we kind of like, yeah, and then like we get the policy. Like let's say that it's like if it's vanilla, if it's just the game state, fine. But if you rotate it, then the policy which we get, we have to flip that too, right? Like that's just being more robust. So like in this case, like if this is our state here, and then we want to get the policy and the value, we want to like pass the state in, then what we can also do is we can like flip a coin, and if it like lands in heads, we pass in this, and then we kind of output that and the value, and then we have like X and we're perfectly fine with it. Or what we can do is we can flip it. If it lands in tails, then we pass in this, we get this probability, and then what we do is we just draw an arrow. Like we take the state, we flip it, we take a policy, and we flip the policy. Like notice this flip, right? if we draw like take this policy here, just like draw like a line there and just flip about, like we basically kind of like reverse it, like 0, 0, 0, 1, 0, 0. We read it backwards, 0, 0, 1, 0, 0, 0, right? Like column 0 becomes column 5, right? Column 1, the very tall one, becomes column 4. Column 2, the one closer to the center, like more medial of this one, more towards the middle, becomes column 3, and so forth. Like 0 maps to 5, 1 maps to 4, and so forth. It's just flipping about this thing. Like it's like 5 minus, or like the formula is like num calls minus call index. Like C prime equals num calls minus C, where like C is the column index and C prime is like the new column index. And then this is kind of like, this function is its own inverse, right? Like if you kind of go from column 1 maps to column 4, and then if this were S and this were S prime, like taking column 4 and then doing like number of columns, like if we're doing like 5 minus 4 to 1, right? Oh, sorry, this number of columns minus 1, minus C, right? It's like 0 indexed. Like for example, 2, right? So number of columns is 6 columns, minus 1 is 5, right? And 5 minus 2 is 3, so like 0, 1, 2, 3. So like this single thing here maps to 3, and like same way, it just kind of flips. So like we need some transformation which will take the state and flip it, and we need some flipping thing that takes the policy and flips it too. So like we need like different flips. Like we need stuff that like kind of flips this way. Like, and like the thing is, like these are actually inverses of each other. Like if we take some S, we do some kind of configuration to it, then the policy, I guess we do corresponding to. So I mean, to be honest, should I just skip symmetry? Should I just skip the symmetry? I guess I'll talk about next time. Okay, let's put that on the back burner now. So anyways, what we do for policy iteration, the whole point is to like generate training data by executing an episode. And then we train it, again, more symmetry here, then like we can skip these. Yeah, the whole point, like the heart of this is this function right here, the self-play, right? So like how do we do self-play for a single episode? Well, we get the starting state in Connect 4, just to empty, all the cells are empty. And then, okay, we initialize search tree, whatever, sure. And while true, until the game is over, that is, like this return state and breaks out of it. Like if the game's ended, then we eventually return. So while the game is not over, we do a bunch of whole bunch of searches to get a refined policy right here, and then like we put that into our examples, right? Because like that's our improved policy here, our training sample. The state, the policy, and we don't know the awards yet. At the end, we assign the rewards. So like we get our improved policy, and then what we do is we sample it, right? Like what we do is we get our action. Like we have this policy here, and then we just kind of randomly choose an index, and we just like kind of we sample it from the improved policy, and then we just transition. We just apply that to go to the next state, and then we keep doing this again and again and again and again and again and again until the game ends, right? Like every single time, like we're given a state, and we do Monte Carlo tree search on the state to get a S is just like the current state. It starts off as like the initial one, and then like each iteration of this this while loop, like while the game's not over, we do the Monte Carlo tree search a whole bunch of times to get a refined policy, and from the refined policy we sample that to get our action, and then we apply the action, and then we get a new state, and it's the other person's turn, and then we just keep doing that until the game ends. And then remember, like every time we got an improved policy, we have to actually like pass it into our examples. Yeah, here's what we do: examples that append the state, the policy, and then none, because we don't know, right? We don't know. Like 0, it's anywhere from -1 to 1. We don't know the actual value. It's only 3 values: -1, 0, or 1, right? 1 or 1, and then 0 if it's a draw, which I guess maybe in Othello, I'm not sure how Othello works, but maybe there is no draws. I don't know. But that's the idea. We just go at the end and we assign the rewards once it ends. Like, because we have a bunch of these examples, and then we just kind of assign them. I guess for me, maybe like what I could do is like, I mean, I don't know, assign rewards a whole, but that's pretty obvious. It's very simple. We just kind of like, based on whose turn it is, like from that perspective, we just like assign the rewards and then we like do a negative of those for the other player, and that's it. Yeah, I think I'll stop now. Like the whole point, I pretty much like what's left is to just do this a whole bunch of times to generate our training examples. Then we train them on the examples, and we keep repeating this whole policy iteration for some number of iterations, and each time the network should improve in playing strength. I guess they did 80 iterations, right? 3 days, 80 iterations to saturate until like they finished. So all that's left now is to do our self-play to get a very strong bot, and then improve our model, our neural network, and then I can play against it. And I've already implemented that. Like once we get the network, like I can easily play against it. Like it just that work is done. I've already plugged in the network to my game. So all that's left is to get a good network. And to do that, we have to do self-play. So I guess like next time, I mean, let's hope that this all comes together. But like again, like this is very few lines of code, right? This is just like what, like 26, like 13 lines of code about, and like the hard stuff is like 22, like almost double that, and that was done yesterday. So like I guess in theory, if everything was done perfectly up till now, then this should be quite straightforward. And all that's left is like just time, because it'll take presumably a long time, many hours, days, whatever, for like the networks to train. So yeah, I'll stop now. That's sufficient.